Okay. Oh, sorry. Thank you very much for letting me speak today. So, yes, I'm going to talk about a project that's ongoing with Luigi Dario Berri at McGill, Serta Donderwinkel at University of Groningen, and Christina Goldschmidt, who's my supervisor. And this will be about the convergence of globally centered discrete snakes, which we'll get to in a bit. So we won't start off talking about snakes, but just about trees. But so what we're going to be eventually looking at are trees with kind of spatial positions for each of the vertices. And the trees that we're going to be considering are size-conditioned bien-aimé trees. So throughout this talk, we're going to let Tn denote a bien-aimé tree with offspring distribution mu. We're going to assume that this offspring distribution is critical, so has mean 1, and has finite variance. We'll condition it to have size n. Okay. We want to think of these trees as ordered, and so this is kind of known as like the Ulam-Harris notation, where we kind of order vertices in the tree with these labels, so 1, 2, 3, and then one's first child is 1, 1. Here it's maybe easier to see 3, 1, 1's first child is 3, 1, 1, 1, and 3, 1, 1, 2. We can kind of continue this on for larger trees. Okay. So just a bit of notation. Throughout this talk, I'll just use psi to denote the offspring random variable, so a random variable with distribution mu. So maybe for those of you that saw Igor's talk earlier in the workshop, there are a couple ways one can encode these trees using functions, and two that I'll go over today are the contour function and the height function. Won't have as nice animations as he had, though, unfortunately. So we'll start off talking about the contour function. So the idea is we have this tree, we want to encode it using a function, and what we do is just trace the perimeter of the tree, and when you encounter a vertex, you record its distance to the root. Okay, so here we start off at the root, then its first child, then we continue, and then we go back down, and then we go into the next subtree, and then we continue all the way until we finally have recorded kind of all of the vertices in the tree. Okay. Now, this encoding is kind of nice because if we imagine placing glue along this function and then squishing it together, what happens is that we recover the structure of the tree. Right? So basically, if you were to take like 2 points in this function and then look at kind of the minimum between those 2 points, that's actually identified with like their last common ancestor. Okay? And this is kind of maybe something we want to keep in mind for what's to come. So this is one nice way of encoding. The second one that I'll talk about, just because I use it a bit more often, is actually just kind of an approximation of the contour function, where we do the same kind of exploration, but we only record distances when we encounter a vertex for the first time. Okay, so again, we start at the root, and we continue this exploration, but here, instead of going back down that branch, we proceed to vertex 2. And we continue in this way, and the exploration stops here. Okay, so this is the height function. Okay, so it was proved by, there was a couple of proofs out there that the contour function is going to converge upon rescaling to a normalized Brownian excursion. And one can then maybe imagine that the trees with some rescaling, though we won't talk about this, will converge to a tree which is maybe encoded in some sense by a normalized Brownian excursion. And for that, you can kind of think about these big trees that are, the limiting tree will be the CRT, but we won't talk about it today. This is just maybe a picture of one of those simulations. Okay. So in our project, what we wanted to do is study spatial trees. So these are the same underlying genealogy, so we still have a bien-aimé tree as the underlying tree, but now each vertex is endowed with a random spatial position. Okay? And there are many ways one could do that, but I'll explain the model that we look at in a moment. So kind of this next section will be more about branching walks and spatial trees. So this is a bit notation heavy, but I promise some pictures are coming soon. So essentially what we want to think about is a family of distributions which are going to tell us how vertices are displaced from their parent if a parent has k children. Okay, so here, this new k is a distribution on the k on Rk, and given our tree, I'm going to assign spatial positions to the vertices. I'll start off with the root, and okay, I'll just say arbitrarily the root has position 0. This is kind of where I'm basing everything from. And then if a vertex in the tree has k children, let's say, u1 through uk, then I can look at the difference between the position of the vertices u1 through uk, so the children, and their parent. This is kind of telling me how far they're displaced from their parent, okay? And I'll say that that vector is going to have distribution uk. So in a sense, it's just telling you the distribution of the displacements away from a vertex with k children. Okay. But in this way, every vertex of your tree is associated with a random walk trajectory, which has the same length as its path to the root. Okay, so basically we start off at 0, and then along, so if we take some vertex in the tree and we look at the path down to the root now, each of those vertices along that path, they've incurred random displacements, and so we have some random walk trajectory, which has also kind of a random length here. Okay, so okay, so in what follows, we'll use yk to denote a random variable with distribution uk. And for instance, basically, we can see that the elements are just going to be yk1 up through ykk. And basically, this is going to mean like the jth child of a vertex with k children is going to have displacement ykj. So in this image, for instance, the parent here has position 4, and then it had 3 children, and maybe those the displacements away from the vertex with this vertex was -12, 2, and -7. So its children are now at positions -8, 6, and -3. Okay, is that okay? Okay. So the genealogy, as we've seen, of these trees can be encoded using like the contour function or the height function. There are other ways of encoding this as well, but for the purposes of today, we're mostly going to focus on the height function and just kind of forget about the contour function, but that's okay. And now we want to find a way to encode the vertices, the positions of the vertices. And this is kind of where the notion of discrete snake comes into play. I won't talk too much, actually, about discrete snakes themselves, in a sense. But what is the discrete snake? Essentially, it's the path-valued process, where basically this phi is going to be the random walk trajectories associated with each vertex. So this is maybe not the right orientation to explain this best, but my drawing skills could only do so much. So essentially, if we look at vertex 0, the root has position 0, so here its trajectory is just 0. Then its first child has position -5, so we see that the trajectory kind of goes down by -5, and we continue exploring the tree in the same way as the contour process, and every time that we see a vertex, we record its path to the root. Okay, so because we're considering kind of linearly interpolated versions, we get kind of a surface here, okay? And so underneath here, what I've drawn, this shaded region, is the area underneath the contour function, right? So this really shows us that these trajectories have the same length, or hopefully visually tells you the trajectories have the same length as their, heights in the tree. Okay. Is there any? Yeah. So what actually will be kind of a bit more convenient to look at is just, maybe I should go back, is just actually this red front here, which we'll call the head of the discrete snake, where we just look at the endpoints of the trajectories. So this is really just looking at the labels of the vertices in our tree rather than the paths themselves. And so this is another way to encode the positions in the tree. So again, we explore the tree like in the height function, and when you encounter a vertex, you record its position. So here I've put displacements along the edges. The edges aren't labeled necessarily. It's just to kind of guide you in understanding how things are changing. But so we start off at the root. It has position 0. We go to its first child. It has position -3, 5, 6, 2, -3, 10. There's a big jump. 1, 9, 1, and back down to 0. Doesn't need to end at 0. This is just kind of an artifact of what I chose.
Just to see if I'm understanding, so that plus 13 on the edge on the right-hand side should be, I guess, a plus 8, right?
A plus?
Yeah, if you, like the second edge that you call.
Yes, I'm sorry, that's a typo. Yeah, my apologies. So Roberto's saying that this this plus 13 should be plus 8. Yeah, sorry. Yes. Okay, so this is a way of encoding the positions of the vertices in the tree. And together with the height process, this is what's called the head of the discrete snake. Okay? And so we'll primarily be concerned with this encoding function as opposed to the snake itself. But later we'll see that actually that doesn't really matter. So what we want to do is achieve some kind of convergence for this encoding function. And to do that, we should expect to have to impose certain conditions on the displacement distribution. So naturally, maybe we might consider a centering condition. So might ask ourselves, OK, does every displacement need to be centered? Do displacements on average from a vertex need to be centered? Or maybe is there some averaging over the tree, and that centering needs to occur? Okay. Similarly, some kind of finite variance assumption, maybe. And then last of all, a tail behavior condition, which is going to tell us maybe how big can my displacements be in order to expect not to get like big spikes or things like that popping up in my encoding when I rescale. Okay, so there's been some work already towards understanding convergence of this function, and they've imposed different kind of assumptions that are in line with these 3 criteria. The first and maybe most natural to consider is just IID displacements, right? So in this sense, basically, our displacement distribution, mu k, is just going to be the law of k IID copies of a centered random variable with finite variance. And so maybe it's natural to expect using or to understand using a central limit theorem type argument, right, that if the height process is on the order root n, well, I have a trajectory now that's about root n in terms of length, and then it's centered with finite variance, so a CLT should tell me that I get some nice convergence there. Okay? I haven't explained what the limiting object is, but I will in a moment. So this is considered by Jensen and Merkel for a critical offspring distribution with finite variance and a finite exponential moment, but it should be noted that also you can remove this finite exponential moment, and this was done in a paper by Narzouk. And so basically what they show is that, okay, if you have the centering and the finite variance, then you're going to get convergence in the sense of finite dimensional distributions, and then that you'll get kind of tightness if you assume this tail behavior condition. Okay? And so what is this limiting object, this R value, this R process here? Well, it's a centered Gaussian process where conditionally on the excursion, it's a centered Gaussian process with the following covariance function. And what does this kind of covariance function maybe, what can we think about here? What's it capturing? Well, if we think back to the contour function, when we placed glue on it, we identified we basically saw that kind of the minimum between 2 points in our function was associated with the last common ancestor, right? And so that's precisely kind of what we're capturing here, that these paths, if I take 2 vertices in my tree, well, they're going to evolve together up until their last common ancestor, and then after that point, they'll evolve independently of one another, okay? So this covariance is just saying trajectories, they evolve together up until there's a branch, and then they're going to do their own thing. Okay, so this was kind of a natural setting to maybe consider first, but it's a bit maybe, we might want to consider more varied displacement distributions. And that's precisely what Merkel does in 2008 with this assumption of bounded support on the offspring distribution. Okay, so the condition that he gives for centering is this kind of global centering condition and a global finite variance condition. And this allows for much more varied displacement distributions. In particular, maybe the displacements here, they can depend on the degree. The displacements away from a parent can be dependent, but displacements within the tree from different vertices are independent of one another, right? And so, right, so this is the condition that's obtained, or this is the kind of same limiting object that we obtain here under those conditions. And the way that this is kind of done is that Merkel kind of proves convergence of the lineages of the tree, and then you can just kind of think of throwing displacements on top of this tree as decoration. And so in order to capture the convergence of all of these lineages, this is where this kind of bounded support condition comes into play. So it gives us a really nice object in the limit, to like a very rich object, but the methods didn't extend to offspring distributions without bounded support. And so, right, so this is quite a nice result, but a lot of the natural models we would like to consider have offspring distributions that don't have bounded support. And so the question that we were kind of asking is, can we remove this condition? And if so, like what are the assumptions on the displacement distributions that we can obtain? So these are our 3 main assumptions. So the same kind of global centering as Merkel and global finite variance, and then a final tail behavior assumption on the maximum displacement away from a vertex with degree given by my offspring distribution. Okay. And so our main result can then be stated as follows. So if I assume that I have global centering and global finite variance, well, then this head of the discrete snake will converge upon rescaling to the object that, like to the head of the discrete snake driven by a normalized Brownian excursion. And then moreover, if I have this tail behavior assumption, so if I make sure that I don't kind of see these spikes then, and on top of that, a third moment condition on my offspring distribution, then I'm going to have convergence in the space of continuous functions with the uniform topology. This third moment assumption is somewhat of an artifact of our techniques, where we have to use a generalized local limit theorem, which requires a third moment. But it's unclear whether or not that's actually the optimal moment condition. So that's one limitation. But at least we can do that. So then, right, so this talks about discrete snakes, but we haven't, I guess we've only really talked about their heads. But the idea is that, well, there's a result by Merkel and Mukadam, which says that results about the head of this discrete snake can then be interpreted in terms of results about the path-valued process itself with the correct kind of rescaling. Okay, and so here on the right, we have the label, the kind of position, the label process, this Rn of a very large tree, and then its associated discrete snake. I've now changed the orientation, which I think is maybe a bit clearer to see what's going on. But the associated discrete snake, And then the shadow that it casts is, again, the area under the contour process. And maybe just to kind of, I think this photo illustrates a bit better why we might call it a discrete snake, right? If we think about trajectories in the tree, well, they're kind of moving up and down as we explore the tree, and it looks kind of like a snake's moving around in the tree. If one were to kind of think about the evolution of one of those trajectories, maybe. Okay, so before I talk about how we prove our results, I'm going to talk about a nice application. And this has to do with the height function and the Łukasiewicz path. So the Łukasiewicz path is another way of encoding a tree via depth-first exploration. So it's the same exploration as in the height process, but instead, when we see a vertex, we record the sum of the number of children minus 1 along that lineage. So I find the easiest way, actually, to think about this is actually just to sum up the number of younger siblings of ancestors we've already seen. In words, that's what's happening, and in pictures, hopefully, I can illustrate that better. So we start at the root, and then we move to the first child, and here we essentially put 2 vertices on the stack, and we move up by 2. And then we continue exploring, well, this it only has 1 child, and so we didn't add anything. Again, this one now has 0 children, so when we go down, we actually remove something from the stack, and we continue in this way. And the lighter green here is always going to be the number of younger siblings of ancestors of the vertex that we're currently looking at. Okay, so this is the Łukasiewicz path. And kind of with this formulation here that I've written, it's maybe easier to see that, like, okay, this is pretty much a random walk with IID increments that are, that's conditioned to hit -1 at time n, right? And so, in a sense, this is quite a nice encoding because, well, IID increment random walks, we can kind of, we can study those maybe more easily than one could study the height process. So there's a bit of a trade-off, right? The height process is giving us nice information about distances. It has a good geometric interpretation, whereas this has maybe is nicer to use, maybe. Okay, and so in 2003, Merker and Mokedem established that for any epsilon, there exists a gamma greater than 0, such that for sufficiently large n, the maximum distance between the height process and the Łukasiewicz path, like the probability that it's greater than n to the 1/4 plus epsilon, decays exponentially like this. Okay? So we might conjecture that maybe actually the correct scaling for the difference between these two encodings is n to the 1/4. Okay? And in fact, that's what it will be, and I'll explain how. So it turns out that the difference between these two functions is a snake, which is quite nice. And the displacements are deterministic. So it's a nice kind of example to look at. So indeed, how can we see this? Well, let's think about first the height process. Okay, so the height, we're just summing along the path to the vertex, to the ith vertex, and we're just incurring the length of the path times sigma, right? So we're just getting sigma times that. And then the Łukasiewicz path, well, we also sum along the path from the root to this vertex, but we're just going to sum up the number of younger siblings of the vertex that we're seeing, right, along the path. So whatever is lying to the right of the path that we'd been exploring. Okay, but that is just, if I think about the number of younger siblings of vertex uj, this is just going to be the number of children that its parent had minus its position within the ordering, right? So this is precisely giving me this kind of number of children minus its position, and then I'm bringing in this sigma here from the height, okay? And so if you had k children, then this thing here is precisely sigma minus 2 on sigma times k minus j. And since I'm summing along this path, this is going to give me the label of that vertex, right? So basically, these are all my displacements in the tree, and then by summing along the path, I'll get the spatial position of that vertex. Is that clear? Okay. So more lucky things is that this discrete snake is globally centered, so it satisfies our first centering assumption, and it has finite global variance, so long as we assume a finite third moment condition on the offspring distribution. Okay. Lastly, we can understand the tail of the maximum displacement using just the offspring distribution. And so this kind of tail behavior assumption that we wanted satisfied is satisfied if and only if we have this tail behavior assumption on the offspring distribution, which moreover implies the necessity of it, or that we'll have a third moment. Okay? So as a corollary of our results, we obtain convergence for the difference between the height function and the Łukasiewicz path, so long as you have you have this tail behavior on your offspring distribution. Okay, so that's one of our nice applications that I think is fun to see first. So I'll talk a little bit about the proof. So the proof is in kind of two natural steps: convergence of finite dimensional distributions and tightness. I think maybe for the purposes of today, we're here to have fun. We'll just talk about convergence of finite dimensional distributions. I'm happy to talk about tightness offline, though. Okay, so this convergence of finite dimensional distributions uses a line-breaking construction, which I'll go through in a moment. So the question we might ask ourselves when we want to prove convergence of finite dimensional distributions in this setting is, okay, how do we construct the tree in a way that is best to understand the law of the positions of k uniform vertices in the tree? This is what I want to do when I study convergence of finite dimensional distributions. So I'll kind of argue that this is through this kind of line-breaking construction. And it's going to be a little notation heavy. I find that normally an example is where I understand it best, which is what's coming. So if you want to zone it out for a bit, there will be just a picture-based explanation in a moment. So the idea is that we'd like to sample a tree, okay? And first we need to we'll sample its degree distribution, or its degree sequence, okay? So we'll sample n IID random variables from our offspring distribution conditioned on the event that they sum to n minus 1. So simply that we'll get a tree with n vertices, okay? Now, what we want to do then is sample a uniform sequence from the following set, okay? This is the set of sequences with values from 1 to n, such that the value I appears, the value I appears psi I many times. Okay? So what we will see is that there's a bijection between these sequences and trees with a fixed degree sequence. So if anything, this is kind of a fun way to construct a tree. I won't talk about the reverse bijection, but just kind of the forward way, and hopefully you can see how to reverse engineer it from there. The idea is that we'd like to chop up this sequence into essentially sticks. And each stick is going to correspond to a path in the tree. Then we're going to graft these sticks together, and the tree with degree sequence psi will be the graph on n with root v1 and edge set given by the union of these sticks. For those of you who are maybe familiar with the line-breaking construction of the CRT, this is a similar kind of idea, and in fact, we want to prove, or in our work, we kind of prove that it converges to that construction. Okay? So to determine the first stick is a bit different than to determine subsequent ones, and it's maybe the easiest to understand. So we take the first value that we have yet to see we can think of traversing this sequence, Vn, and we take the smallest value that we have yet to see. And when we see a repeated value or an instance of the value x in our sequence for the first time, we stop, and we take out all of those vertices that we've just seen, and we make that into a stick. Okay? And then we graft on this kind of lowest value at the end as a leaf. Okay? And essentially, we continue this recursively, where we kind of set our running minimum to be the minimum value that we've yet to put in our tree. And then we kind of continue building sticks and grafting them onto one another. Okay, so like I said, it's a bit notation heavy, maybe hard to see from this perspective, but it's maybe easier to understand with pictures. So here is maybe an instance of one of those sequences. Okay, so the root is going to be given label 3. Okay, and the first time that I see a repeated, and sorry, maybe before I even say that, the running minimum at this point is 1, right? Because from 1 up to 11, without 3, just the first minimum value is going to be 1. So that'll be the value of my first leaf that I put in. But where do I see my first minimum? Or my first repeat? I see my first repeat here at this 2 value, right? So the first stick is going to have length 4, and it's going to be precisely the vertices 3, 5, 2. And then once I see a repeat, instead of putting 2 again, I put the value 1 as a leaf. Okay? Is that clear? Okay. So now we want to put the next stick on. We're going to, because the repeat happened at value 2, the next stick is going to be attached to value 2. Okay? Now, the next repeat that I see in my sequence is, again, this value 2. It comes quite quickly. And so what I'm going to do is, okay, the minimum value that I've yet to put in my tree, it's 4. So I'm going to graft it onto 2 here. Okay? Now, the next stick that I see is going to be 7, 8, and then 3 is a repeat because it's already in my tree. So I'm going to replace 3 by 6 and attach it to 2 because that was where my last repeat was. Okay? I continue in this way. 4 is a repeat, right? So I put 9 and I attach it to 3 because that's where I saw the value of my last repeat, the one previously. And then 6 is a repeat again because it's already in my tree. And then finally, I finish by putting 11 on top of 6. This is kind of an end case that we have to consider because essentially, right, all of the number of times that a number appears in this sequence is going to be its degree in the tree, right? And so 6 has degree 1, so I need to give it this extra child. Okay, does that make? All right, so this is how we construct such a tree with a fixed degree sequence. But you might be asking yourselves, wait, it's really important in the snake, the position of how I put these sticks in place, because that's going to determine the displacement of the child away from its parent, right? So we need some way to keep track of that order, and maybe to construct an ordered version of this tree using sequences. Okay, so one could think of a modification of just sample insertion instructions for the positions, a uniform permutation maybe of the values 1 up to psi I, the number of children that it's going to have, and use that as information for how to glue in your vertices. So if we think about our previous example with the tree that we constructed, instead maybe we would use this kind of input, okay, where, well, now the second coordinate of all of the entries tells me what position I'm going to be putting its next child into. Okay, so I had 3. Here we have 3, 2, which means that 5 will be put in the second position. Okay. Meanwhile, then 5, 1, so 2 gets put in the first position of 5. Then I have 2, 3, which means that 1 got put in the third position. Okay? And we kind of can continue in this way. So essentially, the tree that you just saw in the last construction would have been constructed using maybe this sequence of pairs instead. Okay, so that's kind of the idea there. But it's easier to maybe just explain the non-ordered version first. So in this sense, basically, if we have all of this information, again, putting displacements on is kind of a decoration of some kind, right? We have access to the degrees, we have kind of ordering, and so we know then how we're assigning displacements as we construct the tree. And so this kind of construction will be really useful then to understand the law of k vertices in the tree. So it turns out that it's just kind of enough to study the law of the tree spanned by vertices 1 through k in this kind of labeled version here that we're looking at. And I'll talk maybe about some nice attributes of this construction, which should maybe convince you that, in fact, we'll get the right convergence that we want. So the first thing is that just a fact, right, the subtree spanned by the root and the vertices 1 through k is going to be contained entirely within the first k-sticks. Why does this make sense? Well, in k-sticks, if we haven't basically each time we need to take a minimum value that we have yet to see, right? And so in k-sticks, we're going to either have seen a repeat, which would add k, one of those values as a leaf, or it'll be somewhere within a path, right? So we will definitely have those trees, and we'll argue that, in fact, it's pretty much the same tree. So what we actually can show is that the first k times we see a repeat, or the first, they're going to happen in the first root n entries of the n. So in fact, we're constructing this tree that we're interested in root n steps. Okay? And moreover, with high probability in those steps, we're not going to see the values 1 through k. What does this mean? It means that with high probability, the values 1 through k are leaves of the tree. And so precisely the tree that we're getting when we glue together these k sticks is just the tree spanned by the vertices 1 through k. Okay, so we're building the tree that we want, or we're building something that looks pretty much like the tree that we want, and in fact, with high probability, it is that tree, and we also have access to how many steps we needed to take in order to construct it. Okay? So what we then want to do is maybe think about what's going on this root n timescale. And this will allow us to understand the displacements that are incurred by the vertices. Okay, so on this timescale, actually, one can prove that the out degrees of the vertices, they're asymptotically indistinguishable from IID samples from the size-biased distribution. Okay, so here this is the size-biased distribution because we're assuming mean 1. Otherwise, you would have a rescaling. Okay, so, and moreover, whenever we see a vertex in this construction for the first time, we're gluing its child into a uniform location among its children. Therefore, the displacement that is incurred by the first child that we graphed on is uniform in the displacement vector away from that parent. Okay? So that's this second point here, that conditionally on the out degree, the displacements of a child that gets attached for the first time to the vertex is going to be uniform among those displacements. Okay, so what that tells us is that essentially along a branch, we're seeing IID displacements. These IID displacements are going to be distributed as y psi hat, where psi hat is just a sample from the size bias distribution. Okay, so we have, that's quite nice because now we don't really have to think so much about all these different degrees. We're just dealing with IID displacements pretty much. Okay, so what can we say then? Well, if we think back to the conditions that we had, right? The first condition, global centering, it's actually precisely that this random variable that we're seeing along our lineages is centered. Okay? So now we're seeing trajectories where we have IID jumps that are centered, pretty much. And moreover, this second condition, the global finite variance condition, is actually, in fact, the same as, well, this random variable is going to have variance beta squared. Okay? So we now have kind of IID random variables that are centered with finite variance. And so the only last piece that we need to consider is the effect from the branch points, right? Things behave a little bit differently when we graphed things on for the second time at a vertex, okay? So that kind of causes a little bit of trouble, but in fact, we visit a vertex at most finite many times, and so this has negligible effects. And so what really kind of convince, hopefully, that we get this convergence of finite dimensional distributions is from the fact that if I take IID copies of this displacement random variable, it's going to, and I take root n of them, because I'm working on a time scale of root n, well then when I rescale by n to the 1/4, I'm going to get convergence to a Brownian motion, or beta times a standard Brownian motion, right? And so that's kind of what I should expect to get for my limiting object, because this kind of head of, or like this discrete snake is kind of a Brownian motion indexed by the tree. Okay, or like we can think about the limiting object as a tree on top of which there's this Gaussian process capturing the spatial motion. Okay, so this is maybe kind of a quick explanation of how one could maybe be convinced that this convergence occurs, and that's kind of as much as I think I'll talk about today. So this is just a recap of our results, and thank you very much for listening.